Hello everybody and welcome to tutorial 5 in this series on happy brackets. I'm Garth Payne and today we're going to look at filters and the use of filters to change the frequency content of any audio source that you've learnt to make already. We're going to look at some simple programming tools such as the for statement. In recent tutorials you looked at the if statement, and the for statement is going to let us iteratively loop over a function a certain number of times. We're also going to look at pitch. So far we've just been setting the frequency, for instance, of a wave player. But what if we wanted to play a scale? So there's actually a pitch class that we're going to look at that allows us to construct scales and to play any note in that scale and to force our frequencies to a particular scale. And then lastly, we're going to look at patterns. So far we've made synthesis voices that play a note associated with a clock or something, but now we're going to actually look at having actual kind of sequenced patterns that we can call up at any time that we like during the code. Okay, so let's get on with it. So let's open IntelliJ, and our first port of call today is filters. So just to explain, I'm sure that you're all basically familiar with filters. A filter allows us to change the amplitude of different frequencies within the sound that we're playing back. And so for instance, a low pass filter can be used to allow only low frequencies to pass, and so you hear that being swept down often in dance music as the high frequencies disappear. A band pass filter will allow just a kind of a little band of frequencies, a little mountain if you like, pass, and everything else is cut out and you can move where that central frequency is. There are lots of different filters and we'll touch on that in a moment. But essentially what we want to think about are that these filters, let's say this bandpass filter, has a particular width to the filter, the band that's being allowed to pass through, and it has a central frequency. So if we imagine a curve going over from this hand to this hand, then it has a central frequency point where the amplitude is at its highest, and it has a width of that curve which is called the Q. So those are the two principal functions that we're going to look at. In your tutorial you'll see a pattern class folder, and then in there you're going to see this filters and envelopes patch. Let's just have a very quick look at that. And what you'll see here, if we just look down a little bit, is this biquad filter. So the class that we're using here is biquad filter, and you'll see that we make a new biquad filter, and if we look down here in our help window, we'll see that it takes a couple of different functions. One is the number of channels, the number of audio channels passing through it, and the other is the type of filter. This is where we really get into a very wide range of filter types. We'll touch on that in a minute. Now, I want to add one more thing before we go on and build a patch, and that is that if we just look down here, for instance, this section of the code is slightly different. So we're building a slightly different signal path to the one that you've been used to, where we've had our wave player, we've plugged our wave player or our sampler into a gain object and plugged the gain object into the output. In this case, we need to plug whatever we're going to alter with the filter into the filter itself, and then plug the filter into the audio output. So we put another piece of DSP or digital signal processing, another function between the actual source that's generating the sound and the output. So here you'll see filter.addInput n, which happens to be my noise generator up here, and then gain.addInput filter. So you'll see that the filter is inserted between the noise object and the audio output. Okay, so let's go ahead and make sure you're in this pattern class, and then we will make a new happy brackets sketch. And let's call this filter test. Always start with a capital letter. Oh, I've got too many capital letters. Okay. All right, so there's filter test. Let's start here by just writing biquad filter, because that's what we're most interested in. And here we have a biquad filter. And I'm just going to call it filter in this case equals new biquad filter. And as we know from before, there are lots of ways of instantiating this for different contexts. The one that we want is this one just down here that has a number of channels and a type. So I'm just going to have one input channel, and then I'm going to type biquad filter again, dot type, dot. And so now we're using the biquad filter class, and we're calling the type on that class, and now you can see all the different filter types. Now I'm just going to use this bandpass peak filter, which has a nice curve but has a very clear peak at the top of it. So here is our filter. That's grand. So let's put in a few things that we might use that on. Now I'm going to make a noise object, and you've seen the noise object before, and I'm just going to call it noise, and we don't actually need to put any arguments in there. So noise is going to generate all of the frequencies evenly, and so then we'll really be able to hear which frequencies the filter is allowing to pass and which they're not. Okay, so now we have a noise. So now, as we saw before, we need to plug the noise into the filter. So we're going to filter.add input, we're going to feed it the noise. And so now if we make a gain object, okay, a gain object, and again if we look down here at the various arguments we can provide, here we have the number of inputs and outputs and the initial gain. So again we're just using one input and output, it's mono, and let's start the gain at 0.5. Now I'm going to put an F there because I always try to make sure that whenever I'm putting in a floating point argument, even if it's a whole number, I still put an F after it. Okay, so now obviously we need to plug the filter into the gain object. So we're going to go g.add input, and the input that we're going to add there is going to be our filter. And so here we have our filter, and we've added the noise into the filter, and then we're adding the filter into the gain object. So now we've plugged the gain object into the output, and we're ready to play that audio through. So we've got the noise object plugged into the filter is plugged into the gain object, and the gain object is plugged into the output of Happy Brackets. Now, having said that, we haven't actually set up any of the characteristics of the filter yet. So the first thing that we really need to do here is to set the frequency of the filter, like where is the center point of the filter. And here you can see that if we go filter dot, there's lots of functions that we can call on this filter object, and one of them is set frequency. And you'll see that there are two options here. One is to put a floating point number in. The other down here a little bit further is to put a UGen, which would be an envelope, for instance. You'll also see that we can set the Q here, and again we could set the Q being with a floating point number, or we could set the Q with a unit generator, which again would be an envelope. So let's set it with a floating point number in this case, and we'll just set it at, say, 400 Hertz. Again, it's a floating point number, so I just make good use of the F to make sure that I never forget to put that in. Now let's also set the Q while we're here. Filter.set Q, and again in this case we're going to set it using a floating point number. And so let's just set it to 10 for this initial use, and we'll check that out in a minute in terms of how we can vary both of those using an envelope. Okay, so let's go ahead and compile this, and first we need to start our simulator, and we'll run it off to the simulator. And you can just hear that in the background. Maybe we need to turn it up a bit. Okay, so that's our noise object running through our filter set at 400 Hertz. So let's change the filter frequency to, let's say, 1000 Hertz. And what we should do is we should hear a higher frequency here. Right? And we do. Now, it's the same noise signal going through, but we're filtering it to allow this window of frequencies that are being attenuated from the center frequency, which is 1000 Hertz, and we're attenuating them based on the width of the filter, which is the Q here. Now, at the moment, the Q is 10. If we make the Q very wide, let's say 2, and so a small number is a very wide Q or a very flat curve, a large number is a really tight Q. So let's just listen to a couple of those. Recompile. This is 2, so you're going to hear a really wide filter. It's going to let a lot of frequencies through. And so there, if we change that back to 400 and play it again, you're not going to hear a great deal of difference because the Q is so wide that we're letting a lot of frequencies through here. So you hear some, but it's not that dramatic. Now let's set this Q, instead of 2, let's make it 20 and recompile and send this over. Okay, let's make it even narrower. Let's make it 60. Now recompile, send it over again. And now you can start to hear that we're getting less frequencies. So let's put this up a little bit so it's easier for you to hear it. Back to 1000 Hertz, recompile, send it back over. And you can hear now you start getting this whistling because you've got less frequencies of the noise, and we're starting to get a more perceivable weighted pitch around the central frequency at 1000 Hertz. Let's make this even wider then. Let's make it 100 and see what that sounds like. Narrower. You can hear that gets a little bit clearer. Make it 200. And so on. You can hear that more and more frequencies get cut out. As the number goes up, the cue gets narrower and less frequencies get allowed to pass. Okay, so we said earlier that both the set frequency or the set cue could be set using a floating point number or using a unit generator, which in this case would be an envelope. So let's make an envelope up here, and we'll call this center frequency. And we always need to make sure we're using this beads project envelope here. And that takes just a floating point number to get it started. So we'll start off at 1000, which is the 1000 Hertz that we have it set at here anyway. Okay, now let's add some segments to this. So let's go up to say 3000 Hertz, and we'll do that over 3 seconds. Okay, so now it's at 3000 Hertz. We want it to stay there for like a second so we can actually hear what that frequency sounds like. If we just send a new segment, it'll immediately get to 3000 and then start going to the new place. So I'm going to add center frequency, add another segment. I'm going to make it go to 3000 even though it's already there. I'm going to make it do that for a second. So it's basically going to stay at that 3000 Hertz for 1 second so we can really hear what that sounds like. Then let's make it sweep down. And let's make it go down to say 100 Hertz over say 6 seconds so we can really hear that sweeping. Okay, so we've got this frequency, center frequency envelope that starts at 1000, immediately starts going up to 3000, stays there for a second, goes down to 100 Hertz, and then perhaps we should return it to our 1000 Hertz again. So let's add a segment and make it go back to 1000 over say 1 second. But in order to really hear what it sounds like down here at 100 Hertz, let's do our little trick again and send it to 100 Hertz again for like 1000 milliseconds, 1 second, so that we really hear what it's like when it gets there. Okay, so now we've got this envelope. We need to apply the envelope to actually set the center frequency. So I'm just going to copy cent freq and look down here to where we actually set that frequency. Here, filter, .set frequency, and instead of setting it now with a floating point number, I'm going to set it with that envelope. I'm going to leave this cue fairly narrow. Let's make it 100 so you can hear the effect of that filter sweeping up through the noise and then back down again. So let's recompile that and send it off to the simulator. Up to 3000, now down to 100. And back to 1000. There we go. Let's make the cue a little wider. Let's make it like, let's make it 20. Now you're going to have a much wider envelope. So as it sweeps up and down, you're going to hear a lot more of the frequency content. So let's just recompile that and send it off to the simulator. So you can hear much more of the frequencies as it sweeps up, sweeps down. Okay, and if we really wanted to hear a lot more, we would just make this say 2, and then we're going to have such a wide filter that you can only just really hear any difference at all. So let's listen to that. You can hear it sweeping through, but it's essentially letting pretty much all the frequencies through. So we might think, okay, that starts to sound a little bit like the C, and so in order to make it sound like the C, we might want to repeat that filter sweep a number of times. And this is where the for statement comes in. So I'll just make a bit of room here. So a for statement says that while this condition is true, do the things that are inside that. It's a bit like an if statement, but instead of an if statement which checks, is this true? Yes, do that thing. In this case, we're saying for these conditions, keep doing this thing. So let's have a look at that. So a for statement is basically that. And in this case, what we're going to do is we're going to count up through an integer to make a certain number of loops. So first of all, we need to make an integer, usually called I for the index, and we're going to set that to 0 so we know where our starting point is. Then we have to ask ourselves, how many times do we want this to loop around? And so we're going to say, well, keep looping around while I is less than 4. Okay, and now we need to add a counter to keep adding 1 to I every time that it goes around. And so we might do this in longhand, going I equals I plus 1. However, there's a shorthand here, which is to just go plus plus. And this is meaning take I, it's exactly what you just saw. I equals I plus 1 is the shorthand is I plus plus. You can also use I minus minus if you wanted to start at 100 and count down, for instance. Okay, now we need a couple of curly brackets to make this actually define a function. And now I'm going to put these add segments inside here. Now they're going to complain because we haven't created the envelope yet, so we'll have to drag our envelope up above there so that it's actually created before our for statement. Okay, so what's going to happen here is we're going to generate a new envelope called center freak, and then we're going to add these segments to that envelope 4 times. So what we should hear is now we're going to hear the frequency of the filter sweep up, sweep down, come back to 1000, sweep up, sweep down, and it's going to do that 4 times. So let's compile that and send it over. So that's the second iteration. Third iteration, and the fourth iteration. And now we come back to 1000. Now it's just going to sit on 1000 because we haven't put a kill trigger there to stop anything at this point. So it's just going to keep playing like that forever. It's done its 4 iterations of the for loop, and then it just comes back to 1000, finishes that set of envelope segments and just stops there. So in order to stop that, we would need a kill trigger. Now, one trick here though is that you don't want to add the kill trigger every time you run through this for loop, because we actually want it to do the 4 iterations of the filter before we kill it. So please don't go ahead and add it in here. And that means that we basically need to add it after this for loop. And so if we again get our filter, add a segment, and we'll go back to, we're going back to 1000 over 1 second. And now we're going to add a kill trigger here, a new kill trigger, and we're going to add the gain G to that kill trigger. Now again, it's going to complain because in fact we don't make the gain object until we're down here. So I'm going to take the gain object and paste it up the top here. In fact, we should really also do that with our filter, because as this patch has grown, we've added all these things down here. But we should really instantiate the things that we want to use right at the top of our patch so they're easy to find, and we know what objects are applied here. Okay, so now let's just take out this line here, because that's basically what we're doing. Actually, no, we don't want to do that. We want to leave that there because we want to return to 1000 before this starts happening again. So once that's happened, it's going to go to 1000 again, That's just going to stay at 1000, and after a second it's going to issue the kill trigger. We could make this shorter so it basically does it straight away. Okay, so let's actually just make some of these a little bit shorter so that we don't have to listen to it for so long. Here, I'm just going to make them quite a bit shorter. That should be 500, and that should be 500. Okay, recompile. So it's really going to sweep up and down much faster now. And instead of doing it 4 times, why don't we do it 3 times? Now, although this statement says I is less than 3, it starts at 0. So that means it's 0, 1, and 2. So the integer that you put in here, in this case 3, is actually the number of iterations we will end up with. Okay, recompile, send it over. One, 2, 3, 'comes back to 1000, and then the kill trigger is called and kills the gain, which, as you know, kills everything then in the signal path that's connected to the gain. Okay, cool. So let's just also make a quick little envelope that will adjust the filter. And so actually, maybe we should actually instantiate that up here as well so we can see everything that's in our program in one place. So let's call this set Q, or no, let's call it Q set so we don't get confused. New envelope. And now again, we have to think of the number range. And as you saw earlier, small integers like 2 are a really wide filter. High numbers like 200 are a really narrow filter. So let's start this at, say, 5. So it's pretty wide, but not, no, let's start it at 2. So it's really obviously wide. Okay, cool. Now we'll do this. If we look at this, it runs, well, let's just take this. No, let's add a segment here. So we've got QSet. .add segment, and we'll make this segment go to 200, which is going to be a really narrow filter, over 6 seconds. And if we look at how long we're doing things here, that's 1, 1.5, 4.5, 5, 5.5, and then we've got another 100 here. So we've actually only got 5.5 seconds here. So let's make this actually 4 seconds so we can hear the last part of it. So it's going to go from a very wide filter to a very narrow filter over 4 seconds as this sweeps up and down. But this is actually doing this 4 times. So we actually in reality have, what's that? 5.5 seconds times 4. So actually we could do this over a much longer period. Let's just make it 10 seconds. Okay, and so now as it sweeps up and down, you're also going to hear the Q narrow, and you'll hear a much more defined frequency range as it does that. It's wide, you can hear all the noise. Oh, 1 second. It's not going to do anything at this point, and the reason is we haven't applied it to anything. So obviously down here, we set the Q, here it is all the way down here, we need to tidy up our patch, and at the moment it's just set to 2. So we actually need to set that to QSet. So we're actually applying the filter, which is a unit generator, to set the Q as we go along. Now it's going to change dynamically as we go along. All right. Oh, it's done that very quickly as it gets. Okay, so 200 is really narrow, right? And you can hear that we've gone into this incredibly narrow filter fairly quickly because this is such a high number. Let's change that to 50 and then it'll be easier to hear. 200 is really like extremely high Q. And you can hear it getting narrower and narrower. You'll also notice that as it gets narrower, the amplitude is reduced, and that's because less frequency content is coming through the filter, so there's not as much energy, and so the overall amplitude seems to be less. Okay, so that's a quick introduction to filters. The one thing that we haven't talked about that we'll just finish off with is that if we make another biquad filter here, filter 2, new biquad, 1 channel, and remember we're calling the biquad filter class and then the type, and then we're looking at these types. So here, for instance, we've got high pass, here, low pass, all pass. These are very standard kinds of filters. So if we set this to high pass, then it's only going to allow filter frequencies above the frequency cutoff of the filter to pass. Okay, so we've made a new filter, and it's a high pass filter here, filter O2. And so now everywhere where we see filter down in our code down here, we need to change it to O2. So we're going to set the frequency of filter O2, we're going to set the Q, we're going to take filter O2 and add the noise to its input, and then we're going to send filter O2 out the output. So let's just recompile that. I think I've got all uses of that filter, and send it over here and see what we get. Now you can hear all the low frequency. Okay, in order to make this even more obvious, instead of setting the Q here with the envelope that we set up, I'm just going to leave it as a fixed Q, and let's make it pretty wide, in fact. So let's make it 10. F. Just make sure that you remember when you've got floating point numbers, you don't need it there, but it's good practice to always put it there. Okay. You can hear filter sweeps up, sweeps down, sweeps up. It's cutting out all the low frequencies. Okay, so now let's change that from a high pass filter to a low pass filter and run it again. In this case, instead of allowing frequencies above that point passed, it's going to allow only the frequencies below the point that we're moving, the central frequency. And so on. So what you could do is, instead of using a noise object like I've used in order to allow you to hear all of the frequency content that's being manipulated, you could use a sample player or a granular sample player and run a drum pattern through there and sweep the high pass filter up or the low pass filter down and really hear those kinds of classic effects that you hear in dance music, for instance, quite often. Okay, so that's a basic introduction to filters, and now we're going to move on to looking at pitch and scales so that you can actually play scalar notes on your wave player. Hello, so in this second section of tutorial 5 we're going to look at pitch. And in using the wave player up to date you've been using a frequency such as 200 Hertz or 1200 Hertz. But wouldn't it be nice if we could actually play a scale? So we're going to have a look at that. What I'd like you to do to start with is to open this patch called Melody Pitches. Let's open that and have a very quick look at that. Now some of this you're already familiar with. We're using a clock here, but let's just focus on the pitch content. Okay, so if we look in here, you'll see that we're developing a note, which is an integer, and then we're developing a frequency, which we're later going to put into our wave player. If we look at the note, you'll see that it's using the pitch class with a capital P, and the pitch class is generating MIDI note numbers, which are note numbers from 0 to 127, and each of those note numbers is associated with a particular frequency. For instance, MIDI note number 60 is associated with middle C on the piano, or what's called in MIDI language C3. So we would know that the number 60 is middle C on the piano. Now obviously we can't send that note number 60 to the wave player because the wave player needs a frequency. And so if we look a couple of lines down here, you'll see frequency, and here we're taking this note that we've generated and again using the pitch class to call this function M2F, which stands for MIDI to frequency, and we're passing it the note that was generated up here on the line above. And this function, MIDI to frequency, is going to turn that MIDI note number into its associated frequency so that we can pass that as an input to the wave player. Okay, let's look at a couple of other things. So we're going to be using the pitch class with a capital P, and it has lots of functions that we can use. You'll note here that we're not instantiating a new version of that pitch class to make a new object. We're just using it directly. So our integer note, which is our MIDI note number, is immediately just pitch dot, and then you'll see here force to scale. And so force to scale is going to take whatever note number appears in here and force it to fit whatever scale, which you'll see is defined here as a variable in this function. So why would we do that? If you look up music theory, you'll see that each of the scales contains a particular subset of the 12 semitones that occur within an octave in Western music. And usually they're only using, say, 7 of those pitches, not all 12, or in a pentatonic scale, only 5 of those pitches, not all 12. So then if we're generating a frequency, we need to work out, okay, which is the closest note to that frequency that actually fits the scale that we want to use. And this is how we are able to play scales and generate melodies. So this force to scale function is extremely important. So they're the two most basic parts of the pitch class we're going to look at here. So let's apply those in a new patch. Okay, so make sure that you've got this folder selected, or perhaps your own folder of patches, and then go new, happy bracket sketch, and let's just call this pitches fun. It should start with a capital letter though, because we're actually making a class, so pitches fun. Okay, and there we go. Okay, so let's make a new patch. Just make sure that you have selected the folder that you want to put this in, and then we will go new, happy bracket sketch. And let's just call this, we need to start with a capital letter, pitch fun, make a little melody. Okay, so here we are. So we're going to need a bunch of things here to make this work. Okay, so we're going to need a few things here. So let's start with a wave player as our sound source, new wave player. And if we look down here, we're going to need a frequency, floating point number, and we are also going to need a buffer. Let's just use a sine tone. Okay, now we should really make a gain object here, and we need to just set that with the number of inputs and outputs and a starting point in terms of the gain that we're setting it at. and then we could basically just put those things together. hb.sound, G, send the gain object out there, but of course first of all we have to add the wave player to the input. Okay, so now we have a wave player, gain object, we've added the wave player to the gain object, and we're sending that out. So let's just have a quick listen to that, make sure that that works. And indeed it does, and we're very familiar with that. So let's put all of that in a clock timer, and so we'll just take all of that code and we'll drag it up here. And now of course if we play that, it's just going to generate a new wave player that's playing indefinitely and it's going to make a new one every twice a second. So we really need to make an envelope, and if we look down here we're going to have a starting point. I'm going to make this the amplitude envelope, so I'm just going to start it at 0. We need to add therefore an attack phase, so let's make it come up to 0.5 over 50 milliseconds, and let's keep it there at 0.5 for 100 milliseconds, and you'll see that I need to put an F after each of these, and then we'll bring it down and kill it. Now we're going to kill the gain object, so we need to add this segment after the gain object has been created, and we're going to bring it back to 0 over 100 milliseconds, and we're going to add a new kill trigger here, and we're going to kill the gain, and we'll put a semicolon at the end. So now we've got starts at 0, goes up to 0.5 over 50 milliseconds, stays there for 100, goes back to 0 over 100, and is killed. So that's a short note, and in order to hear that actually take effect, we need of course to add this envelope to the gain object itself, because at the moment it's just set at 0.5, and so what we need to do is add E in there so that it's actually being controlled by the envelope and not by a static number. So we'll recompile that and play that, and we should hear individual notes. And indeed we do, and there they are at 300 Hertz. Okay, so wouldn't it be nice if we could make that play different pitches? So the first thing that we need to do is to make a note. Now the pitch class, as I mentioned before, is going to generate MIDI notes, numbers from 0 to 127. We happen to know middle C is MIDI pitch number 60. So what we're going to do is to generate here a pitch, and we're going to force it to a scale, and I'm going to set a fixed note number here, 60, oh not 560, 60, and then I need to tell it what scale that's in. So again we use the pitch class, and we're going to go dot, and here we have a bunch of scales, major, minor, Dorian, pentatonic, etc, etc. Now as I mentioned before, the scales are a subset of all 12 semitones that occur in the octave range of a musical instrument in Western harmony. And within that subset, if we take for instance a major scale, there are 7 notes in that. You know, C, D, E, F, G, A, B, 7, and then C again, 8. If we take a pentatonic scale, there are 5 notes in it. So what we need to know is that when we're forcing this pitch into a scale, it's going to select from the 7 notes that could be in that scale. So let's just select the major scale, and there we're going to get a MIDI note number, 60 in this case, forced into the major scale. Now in order to put that into the wave player, we actually need to have a floating point number which is in frequency in Hertz. So let's make a float here, and we'll call this just frequency. And now what we're going to do is again call the pitch class, and to call a function here, and there it is, M2F, MIDI to frequency. So we're going to feed it our note number, which is a MIDI note number, and it's going to turn that into an actual frequency in Hertz. So now what we need to do is we need to plug that into our wave player down here, and so now we're going to have this playing the note number 60, which is middle C, obviously repetitively. But it's a step forward because now we can actually start to think about changing the note number. And there's note number 60. Now I happen to know that the G above that, if we go C, D, E, F, G, is note number 67, 7 semitones above. And if we compile this and send it again, we're going to hear it playing G, etc. So we could use the for loop and generate a number of notes played followed by a number of other notes, etc., etc. But in this case, let's actually use a random function. So in this force to scale, what I'm going to do here, is to use the hb.random number generator, okay? And then we want to get the next integer, and we're going to choose an integer range that is the number of notes in the scale. In this case, 0 to 7, or 6. But anyway, yes, 7 with the... Okay, so we're going to randomly choose a step in the scale, and we know that the major scale has 7 notes in it. So I'm going to bound this by 7. Now I don't want to play the bottom 3 notes, so I'm going to add to this, let's add 60, which is, we happen to know, middle C, and so now we're going to choose the notes of the middle C scale around there. And each time this plays, it's going to choose randomly a note in that scale to play. Here we go. Okay, so obviously we could then start thinking about changing this note number 60 by changing the octave, therefore, that we're playing in. So if we were to take this down an octave, then we might go to 48, which is 12 semitones lower, recompile, and now we're going to be playing the same set of pitches, the same scale, but starting an octave lower. And if we went up 72, 12 semitones higher, we'd be playing the same scale again, just that select 7 notes in the major scale, but an octave higher. And equally, we could then decide, okay, we don't want the major scale, we want to play the minor scale, recompile, and now we're going to have notes just from the minor scale. And note that we haven't changed anything else in the patch. Okay, so that's playing now notes in the minor scale. Just note that it's a little catch here, and I'm going to do it so you can see the error come up. I'm going to select pentatonic, but the pentatonic scale only has 5 notes in it. So if I compile and run this, it's going to crash, because it's going to try and select up to 7 notes, and there are only 5 that are available. Let's see what happens here. All right, well, we're lucky here, but what we should have done is to change this to 5 so that we don't go outside the bounds of the scale. And again. Okay, so we've been playing notes randomly. Let's work out a way to play them sequentially up through the scale. So the first thing we would want to do then is to go into the generation of our note and change this so that it's not just generating random. So let's call this step. Which step of the scale are we on? So obviously we need to generate an integer somewhere that allows us to generate this number as we go through. Now, if we place this inside our clock, we're going to regenerate that every time, which we don't want to do. And so I'm going to generate an integer called step, and I'm going to set that to 0. Now, this is not going to work, but it's useful to go through this to show you why and how to fix it. So here we've generated step, we've put step in here, and now after we've generated our note and played it, we want to add 1 to the step so that we know that we should move on to the next step in the scale. So I'm just going to put here step plus plus. Now you'll see that that's underscored, and if we look at what it's saying that's wrong, it's going to tell us this strange thing about it should be final or effectively final. And if we now go and try and compile this, it's going to come up and show us that exact error here, auto build with errors, and it's going to say again that this should be final or effectively final when it sees this step. Now, the challenge that we've just come up against is about the scope of the variable. In other words, when we go to use something that's happening inside our clock here, we have a particular scope inside these curly brackets that go down to there, and we haven't made an integer inside here called step. So it doesn't really know where it should refer to. In addition to that, because it's sitting here, it can only really occur inside the scope of that particular function, this happy brackets action. And what we really want to be able to do is to use that step function in any of our various functions or as a variable anywhere in our patch. So what we're going to want to do is to take it out of here. Let's just cut that out of there and make it what's called a class variable. In other words, right up here where we define the class, we're going to pop it in there and make it a variable that's available to everything that we write within this class. And you'll see once we've done that it turns pink, which tells us also that it's recognized here. So now let's compile that. It compiles. So it starts off at 0. Each time it goes through this clock, it's going to add 1. So it's going to go 1, 2, 3, 4, etc. That number that gets put in here is essentially the semitone number of the scale. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And that's going to be forced into this pitch class major scale. So you're going to hear some repeated notes because it's going to look at the number and say, well, hang on, that's closer to this note than that note. Okay, here we go. So let's compile, recompile, and we'll send that off to the simulator. And you'll hear it counting up through the scale, but playing repeated notes. And it's just going to keep on doing that. So let's just do a couple of things here that might help us. The first is, instead of showing the MIDI note number, let's show the step here so we can actually see the step of the scale that we're actually working on. The other is we mightn't just want it to keep adding up forever, and so we're going to use a couple of the skills that we've found, that we've learnt previously. So we're going to say if step is less than 12, which would be an octave, or we could make that 24 if you like, then add go step equals step plus 1, or in shorthand step plus plus. But if that's not true, else, then we're going to say step equals 0. So if it gets outside that range, we're going to reset step back to 0 so that it's constantly cycling through this range. Okay, so let's recompile that and send it off, and you'll hear exactly that working now. And there we go, back around to the bottom again. And so if we set this to 12, it would only do 1 octave, and let's set this to be much faster. 200 milliseconds, oh well, let's make it double the tempo, 250 milliseconds. Recompile and send that. And now you can hear it stepping up through the scale. And doing so just through the octave and repeating the octave. And so that's a very simple way just to go up through the scale step by step. Okay, cool. Now there are lots of ways of dividing the clock and generating other rhythms in here, but the purpose of this particular section of the tutorial was to introduce you to the pitch class. I want you to note that you don't need to instantiate or construct a new object. We're just calling functions from the pitch class. So we're making a MIDI note here. Remember, this is going to be a MIDI note, and that's going to be in the range of 0 to 127, and you can look those up online and find out which notes refer to which particular pitches. And then we need to convert that MIDI note to a frequency in hertz in order to put that frequency into the wave player here. Okay, that's a basic introduction to the pitch class. Just before we leave the pitch class, I wanted to show you the use of the status here in our simulator to look at that pitch. So here we're generating our MIDI note number, and let's just go hb.setStatus and we'll call it the note and leave a little space plus note, which is this actual number that we're generating here. So every time it selects a new note, it's going to tell us what the MIDI note number is. Maybe we should make this MIDI note number so it's really clear what we're looking at here. Recompile, and it's going to tell us what note that is, so let's just do that. And here you can see the note number is being displayed in the status window, and that can be really useful for troubleshooting and for just checking what's actually going on, and for instance checking how often does it call that note, and if you're making a scale, making sure that they're all played properly. Okay, so that's how we can select notes in a scale, and then we can set a root note that we're adding those pitches onto so that we could easily change the octave that we're playing in. So keep in mind that you're using the pitch class, that you can force the frequencies or the note numbers to a particular scale, that you can select a whole variety of scales in there, just pitch dot and then you'll select the scale. And keep in mind that at the moment we're using those to generate notes, but you could equally be using those to send a filter, to have the central frequency of the filter mapped to a particular pitch of a scale, and to be moving that filter with the notes if you wanted to. And this is a technique that can be used in synthesis to generate additional resonance and so on in the note. Okay, the other thing to remember is that you need to convert that MIDI note number into a frequency, and we use the M2F MIDI to frequency function pitch.m2f and feed it the note number, and that generates the frequency. Of course, the opposite is also available, a frequency to MIDI function. So if you're generating other content, let's say numbers coming off a sensor, and they're higher numbers that you might scale into a frequency range, but you want to force those into a MIDI note in order to force them into a scale, then you could use the frequency to MIDI to do that, and then generate a MIDI note number that's forced into the scale and then convert it back to put it into your wave player. Okay, let's push on, and the next section of this tutorial will deal with making patterns that you can use for sequencing. Okay, hello, and welcome to the third and final part of this tutorial. In this section we're going to look at patterns. So up to this point we've instantiated clocks, we've put code inside a function, a clock function, and then we've looked at how many ticks are within that clock count, and then we've played particular things on those divisions of the clock, for instance. So these have been very simple. They might include a scale, they might include a randomized pitch, they might include playing a sample, etc. But essentially, once that function starts, it plays and then stops again. We can't then call it back at a later point in the program. So as those of you who are used to sequencing MIDI or audio in a digital audio workstation will be very familiar with, we usually want to have material that we can call up at any point in our project, and or based on sensor input or other kinds of if statements, so that we can play these particular patterns, and they're called patterns. So in this section of the tutorial we're going to look at patterns. Now patterns are made using the kind of mother of all of the classes that we've been looking at, using beads. And the bead is really an abstract class, and every time you go to make a new object you see that you're actually selecting it from the beads library. And the beads abstract class is defined to start and stop, pause and send messages and so on. So it has particular behaviors that are common across all of the objects that it controls. The messages can be sent from one bead to another, etc. And of course you've seen this because we've already been using the message receive function, which actually receives, say, the clock tick and allows us to do something with that. In addition to that, you can pause a bead, and that means that it will no longer respond to any incoming messages. And this is what's called a Boolean, so the pause is either true or false, and you'll see that in a moment. Of course, we can also delete a bead, and you've seen the kill trigger, and the kill trigger, as you know, deletes the object and everything else in the signal path attached to it. And then we have the UGen. So everything that runs at audio rate is a UGen, or a unit generator. And so this is a really critical subclass of the bead class. And this is what we're actually going to do. What we're going to do is we're going to pause or unpause our UGens. And when we do that, they stop calculating audio, so they stop sending audio. However, what's really different here is that they don't get deleted. So if we use a kill trigger, they stop sending audio, but they're gone, and we would have to recompile to get them back. In this case, we're just pausing them, we don't delete them, they're still connected, and then we can unpause them and play them again. Okay, so let's get on here and just open this pattern starter patch. And I want to show you a few things here, key things before we get started with building our own patch. The first is that you see here bead, and I'm just calling this melody pattern. If we click on this, it'll show you that that's made from a new bead. And that new bead has a message receive function. And you'll see it receives a bead message. So these are exactly the things we were just talking about. The bead class, the abstract class handling messages, the message receive, receiving a bead message, etc. Now then I've got a simple patch, you've seen all of this before, which just generates a note. That note is then used in a wave player to play a little melody that's generated randomly here, happy brackets, dot random number generator, dot next int. So let's just compile this and play it. Okay, now one thing that I want to point out here is that I have my computer here running as the simulator, but I also have a Happy Brackets device running over here on my desk. And so here you can see it running on the desk. Now, if I just go up here, having compiled it, and say send to all, it's going to play both on my computer simulator and on the Happy Brackets device attached to the network. Both of these are attached to the PiNet network. Now, we could have any number of these devices, 1, 1,000, it doesn't really matter. So long as they're attached to the network, they'll appear in this list here. So let's send it and see what happens. And so you can hear the audio of the desk. So you can hear the audio of the one that's sitting on my desk and my computer running at the same time. Okay, so that's one little example of just sending this melody pattern over. Now if we look at the top here, a couple of other really important things. Obviously we need a clock. We need to know when this is running both on the computer and on the Pi hardware. And so here you'll see clock. This is very familiar to you. HB create clock, interval 500, start the clock. Now this would normally be created using the clock timer. And let's just do that. And you'll see here exactly this code, clock equals HB create clock interval 500. And so we've just taken that section of the code and left it there and removed the rest. You'll also see here clock.start to start the clock, and we have that here. Now this other section, which is where we add a clock listener to the clock, is really important, and I'm just going to delete that so we don't get confused by it, and skip down to the bottom of the patch where we're going to see that code pasted in here, clock.addClockListener. And in there you'll see my melody pattern, there it is, melody pattern, and you'll see that I've added dot message null. So what this does is it connects the melody pattern to the clock so that the clock is now sending messages into the message receive function here. And then below that you'll see that I've taken my melody pattern again and I've gone dot pause false so that it plays. So let's just change that to true, so you remember that it's a Boolean. So if we set this to true, then it's saying yes, it's true, it's paused. Okay, let's recompile this and send it out again. Okay, and we'll send it to everything again. And of course we don't hear anything because all of this code is sitting inside our pattern, and our pattern is now paused. So now you can probably extrapolate from that to imagine therefore that we could use a clock, and at different divisions of the clock or counts of beats we could unpause that pattern or repause it, and we could have any number of patterns that we like. Okay, so let's make sure that we're in our folder here, and we'll go and make a new Happy Brackets sketch, and let's call this just pattern test. Okay, so here we are with a brand new empty Happy Brackets class. So the first thing that we want to do then is we want to make our pattern. So if you remember, it's a bead, right? So you'll see here bead comes from the bead project.beads.core. So this is the fundamental class, abstract class here. And so now we have a bead, and I'm going to call this pattern 01. And then I'm going to say equals new bead. Okay, and when I do that, it's going to tell me, hey, you need some other methods. You need to sort out what you're doing inside this bead, because as we've already talked about, it can do lots of things, and you see them listed here. Can pause things, kill things, you know, etc., etc. So in this case, we want a message received. We want to receive the clock message, in fact, so that we know we can synchronize and play things in here. We don't need this super message received here. Okay, cool. So now we're just going to go ahead and create a clock, because in order to play this bead, we'll come back and put some code in here in a minute. In order to play this bead, we're going to need a clock. So let's just write clock timer, and of course we get this whole function. And if you remember, we want to create our clock at an interval of 500, but we don't need any of this code up here. So I'm just going to delete it and put a semicolon at the end of that line. And so there we have a clock, and we've created the clock at an interval of 500 milliseconds. Now, down the bottom here, we actually want to attach our clock listener to our pattern, right? So what we're going to do is we're going to paste that code that we just took away from up the top there, and we're going to go clock.add clock listener. And now we already have a function brackets here, and we can put our code in here. Okay, and here we already have curly brackets for our function. So now we're going to take our pattern 01, I'll let that auto-complete, and we're going to go .message, so that it's going to attach it to receive the bead message, but we're going to tell it initially that there is no bead message by using null, and null just means an empty variable. Okay, so now that is attached to the clock listener, and so now we're going to get ticks from the clock, which is of course what we need when we want to play something here. Now, there's a further thing that we need to do here, and that is, now that we've got our pattern and our pattern is receiving clock ticks, we need to pause our pattern. So we're going to go in here and we're going to go pattern.pause, and we're going to write false. Well, if I could spell correctly, we would write false. Okay, so pattern 1 pause is false, which means that it will play, it will receive the messages, and it will do whatever we want it to do. Okay, so this is the kind of infrastructure for patterns. So let's go into our pattern here and do something that's kind of a little bit more interesting. Okay, so the first thing that we might want to do in here then is to get the clock. So let's get clock.get number of ticks, and this is like every time it sends a tick it'll get one, and then we're going to ask that is that like, if let's go modulo 16, which would be once every beat, equals 0. So what we would really want to do is wrap that in an if statement. If clock get number of ticks modulo 16 equals 0, then do something, play our sound. Okay, and so in here we're just going to do our normal thing. Okay, so inside this clock we want to do something. I'm just going to go back to our pattern starter, and just for the sake of speeding things up, copy this playing here, synth, and put it in there. And it's going to tell me, oh, there's a whole bunch of things that you need to load. And of course it's correct. So we just go, yes, okay, and there we go. So here we're generating a note using a pitch, force to scale. We're writing the MIDI pitch to the status over here. We're generating a frequency in hertz using the MIDI to frequency, plugging that into our wave player along with a sine wave. And then we're generating an envelope, which is going to control the amplitude of the envelope. It's plugged into the gain object here. And then of course we're killing that at the end we're adding the wave player to the gain and putting the gain out. And we're doing this when the clock division equals 16. So typically in these environments, the beat is divided into 16 divisions. Using the code from the clock timer, we're actually just sending the beat without the division. So every 500 milliseconds or at 120 beats per minute, we're sending a beat. So what we actually need to do is to go up here where we've got our interval and divide it by 16 so that it's actually sending much faster ticks. That is 16 per beat at 120 beats per minute. So let's just compile this. Okay, and we need a semicolon there. And let's send it off to both of our devices. And so now we have a pattern which doesn't automatically play when the code runs. It only plays because we set this pause to false. If we set this to true, if I could spell, okay, if we set that to true, reset everything, send it again, nothing is going to play because we've set pause to true, which pauses the pattern. No sound. So now we can quite easily go and make a pattern 2. So I'm just going to copy all of this pattern 1, pop it down here, and I'm going to call it pattern 2. And instead of having a sine wave, I'm going to go buffer.saw. So we have a saw wave, and then I'm going to lower the pitch by 2 octaves, which will be 24 pitches. There are 12 pitches in each octave. So that's going to be 36. And so this is going to be our bass note. And rather than having that play every division of 16, I'm going to ask it to play every division of 24. So we're going to get slightly different timing pattern going on here. Okay, we'll leave it basically the same length. Everything else will work here. Now, because these are inside different functions, we can use the same name, wave player, e-gain, etc. without problem. Now, of course, we need to now add a clock listener to pattern 2. And so we'll send the message there also. And we need to say whether it's paused or not paused. And so let's set that false. And now what we should get is that we should get pattern 2 playing, but pattern 1 is not playing. Okay, recompile. And we'll send that off to both devices. And you can hear our low frequency saw wave bass. Okay, so let's set this to false. In other words, pause is false. In other words, it will play. Recompile, and now we're going to get both patterns playing. So at this point, we're just playing them when we start the code and not doing anything else with them. So let's take a look at what else this opens up for us to do. Okay, so in order to start and stop these at different times, I'm going to generate a counter. So up the top here, I'm going to make a new int, and we'll just call this counter equals 0. And we've looked at this before, but now we're going to apply it in a different way. And so I'm going to make a separate bead that doesn't make any sound. It just manages when to turn these things on and off. So here, above our clock setup, I'm again going to go bead, and I'm going to say sequencer equals new bead. And again, it's going to ask us what do you want that to do, because it's an abstract class. I'm going to say, yep, I want it to have a message receive here. And you can see down here this little red line which is telling me that we actually need to have a semicolon there. So let's fix that now. Now what I'm going to do is I'm going to ask it, I'm going to say if the counter is less than 10, and now we're going to put these up here. Play pattern 1. So pattern 1 pause is false. In other words, play pattern 1. And then I'm going to say, and you could have all kinds of conditions here, obviously. I'm going to say if, actually let's make that 8. So we'll get 8 bars of that. And then every time we play that, of course, we need to add to the counter. So we're going to go counter plus plus, which is the same shortened variation of counter equals counter plus 1. Okay. Why doesn't it like that? Oh, I know. So this is a good thing for you to see and to learn from. And you'll see here that it says the variable counter is accessed from within a class and needs to be final or effectively final. Now you'll remember that up here I told you that within these patterns it was fine to have the same names for things like wave player, envelope gain, etc. because they're within their own function and the scope of where they're defined doesn't cross over with the other pattern up here. So this is the same here, this is defined in here, and actually it doesn't know where counter is, even though I put it up the top here. So what we need to do is we actually need to turn this from being inside the action to being a class variable so that everything within the entire class can access it. And what we're going to do is to pop it up here above override, and that will make it a variable of the pattern test class rather than a a variable within the action. And now we should see that those red lines have disappeared, as they have. Okay, so every time it goes in here, it's going to do something and then it's going to add 1. What I should say is we don't yet have a way of telling it when to do that. So we're receiving this message, and further down, of course, we're going to add a clock. So we need to do the same thing that we've done here, which is to give a timing structure for when this is actually going to happen. So let's just go ahead and do that. And that's going to, of course, cause everything here to get upset. So let's fix that. Okay, so now we have a clock function. We're putting all of this within the clock. So I'm going to say if the clock equals 32, which would be every 2 beats. So if clock.getNumber of ticks modulo 32, so divide it by 32, and if that equals 0, which is every 2 beats, do the things that are inside here. Okay, so counter, and the counter starts at 0, and so it's going to be less than 8, etc. Now there's one other thing that we really need to do in both of these, and that is, as you might remember early on, we talked about the bead class. And what I didn't tell you is that when a bead is generated, it is automatically active. It is not paused. And therefore, without putting in a call here to actually pause pattern 2 would otherwise be active. So what we're going to do here is just go pattern 2.pause, and we're going to say true because we want it paused there. In here, we're going to go pattern 2.pause false, because we want it to play here. Now again, we'll just copy all of that, else if, etc. Let's get rid of that extra line first, and we'll go another 8 bars, or another 8 beats, and go 24. And in this case, we're going to pause pattern 1, and so pattern 1 is now paused and pattern 2 is playing. So we start off with pattern 1 playing, pattern 2 paused. Then we play them both together, then we pause pattern 1, and we continue to play pattern 2. Now at this point the counter will get to a certain number and then just never change, in which case we'll get stuck in here. So I actually want to place another else if statement here, and we're going to say if the counter is greater than or equal to 24, then the counter equals 0. So we're going to reset the counter so the whole thing can start again. Okay, so here we have a bead which we've just called sequencer at this point, which is turning on and off, or pausing and unpausing these patterns. Now note that at no point do we kill the pattern off or kill the sound off. They're always sitting there, and we could put something else down here that says, you know, if the counter equals, well, if we didn't set it to 0, if the counter equals 72, start playing again. So we can really set up these patterns of playing and sequencing of patterns. So we don't want these down here anymore because we don't want to set the patterns to be false. In fact, it could be a good idea if we do set them to be true, which means that we start by pausing them both. And the reason is that we might otherwise get a pattern starting before we get in here to set it to be true. Okay, let's recompile that. Okay, and we still have the device sitting here, the second device, so you'll hear both. And here we go, send to all. And there you go, we've gone greater than or 8. So now we add the bass line. And now after 8 bars, we stop the melody and we play the bass line, and now we're back to 0 and off we go again, and it'll just continue to do that. Okay, now I want to add one more thing before we finish this. So earlier on we found that we could find out the ID of the device, and if you look over here, each device has an ID 1 and 2. So the device on the table is ID 2, the device here, my computer, is ID 1. You'll notice that they're negative, and that is because, as you'll learn, you can actually set up a series of devices that are known to IntelliJ and to the code that you're writing, in which case their ID is positive. But if in this case we haven't set that up, then their ID is going to be negative. So we could actually then go and get that number here. So I'll just go int index equals, or let's call it my index just to be a little more appropriate, equals hb dot, oh actually no, we shouldn't do that because that's the actual function, sorry. Let's call it id equals my index. So that's going to go and get the index of the hardware itself, these -1, -2 numbers, and display those for us. So that's very helpful, and we're going to use that in a second. However, we don't really want them to be -1 and -2. We want to make sure that they're positive. So in order to do that, we're going to use the math class, and we're going to go absolute, and then we're going to put hb.myIndex inside there. And what that's going to do is that when it gets that index, it's going to turn it into an absolute number, which is a positive number. So they're going to return +1 or +2. Now let's just make sure that that is the case by going hb.setStatus, and we'll call this my ID plus ID. Okay, and that's going to write here in the status window where it says reset the ID of each device. So let's just compile and run that. It's going to get overwritten by other things, so watch carefully so you can see that as it starts. There it is, my ID. And then of course the counter starts to do its thing. So let's use that as an additional clause down here. So where we've got this counter, we could say, for instance, here where we're running both, instead of running the second one on both, we could put in here if ID modulo 2, so 2, if you divide by 2, if it's an even number, it will produce, it'll be true, ID modulo 2 equals 0, then we will play this pattern 2. In other words, we're only going to play pattern 2 on the even numbered devices. And so now if you had 30 devices here, it would only play it on the even numbered devices right across. So this is very quickly extensible. And then what's going to happen here is that it's going to just pause both. So let's just do that, and we'll only hear pattern 2 played on ID number 2, which happens to be this hardware that I have sitting off here. All right, so let's run that. Send to all. So they're both playing pattern 1. Count to 6, 7, 8. And there's the bass, and it's only playing on the external hardware at the moment, ID2. And now, because this is set to be false, in other words to play, and I haven't set an ID, pattern 2 is playing on both devices. And now we go back to the beginning. Okay, so that gives you an insight into how we use patterns. I'm going to have a little quick look with you here at a patch that I've put in for you called Melody Folk Tune. And you'll see here, basically, I'm not going to go through the whole thing with you. You'll see lots of things that you're familiar. The kind of clocks that setup that we just talked about. You'll see tap in, tap out, because there's some delay here. You'll see a bead called bass melody. You can guess what that is. And again, we're getting clocks. So we're doing that every 64. So every 4 beats, we're playing a new bass melody. We're adding that into the tap in. So we get delay on it. Then we have melody 1 here, melody 2, and then we have what I've called melody transposer. And so here we've got various loops, and then here we have what I call a bead called melody transposer. And inside here we're using a loop counter, which of course we've set right at the top here, to play certain things, but we're actually using it here to change the bass frequency. So the bass frequency I've set at 24, and so we're using it to transpose the bass frequency, which is part of one of these patterns up here, and there it is in the bass, actually in the bass melody. So we're transposing the bass melody up and down, and of course you could add that at the same time as starting and stopping beats here. Okay, so let's just have a very quick look at this and play it, and so you can have a listen to that. Okay, so let's have a listen to that. Let's compile it and send it to all hardware. Of course, you could also divide these melodies to only play on certain devices with an ID that's odd or even, or every fifth device, or whatever you want it to do. Okay, so let's send it across and have a listen. And what you're going to hear is that obviously these start at different times because the clock division here is different. 32. And then this is transposing or adding to the clock every 64 ticks. And you can hear the transposition of the bass note going on there. So let's just be absolutely certain of that by taking the bass frequency here and reporting it into hb.setStatus, and we'll set the bass frequency so that you can see the bass frequency written into the status there, and keep an eye on the transposition that's going on. Let's reset, and one last time. There you go, so the bass frequency is set at 32. And now the bass frequency is set at 39. Now 36. And now down to 24. And then at this point, it'll reset the loop counter. And we will start all over again. Okay, so that is a basic introduction to patterns. You will find further patterns in here that you should play around with. You'll find exercises to do, and you should really think about this as your method for sequencing content. And of course, you can also then use this to say, well, if the device is turned on its side, then play pattern 1. If it's turned on this side, play pattern 2. If it gets a message from another device that it's been turned, then play the 16th beat hi-hat pattern, etc. So you could start to think about how you could use the network of devices to play patterns that are associated, that are in the code, that are sent to all the devices, but only certain patterns play depending on the ID of the device. Okay. Enjoy!